Welcome. There are two different ways how we can approach the question whether something happens typically. One is using probability theory. We can say something happens with probability 1 or with probability 0, that would be rare, or we can use topology, which doesn't need a measure, but we just say something happens generically if it's a bare generic, meaning that it's the intersection of a countable set of open dense sets, and that has to be then dense in a reasonable space, like a complete metric space. And many spaces of dynamical systems or operators are complete metric spaces, so one can use this bare category tool. I just wanted to mention a couple of things. First of all, there are two playgrounds. One is classical dynamics, where you are looking at a system, and this defines an operator, a unitary operator. A function goes into f of t, and then there is the quantum dynamical approach, where you just look at the operator, maybe e to the I h, where h is a self-adjoint operator. Then we have a unitary operator. We can ask what happens typically. And there is this wonderful theorem which I learned when I was at Caltech, which is just at the time when I was there. Barry Simon was proving this wonderful Wonderland theorem, which says that if you have a space of operators with a strong operator topology, can be also a little bit weaker, then what happens is if you have a dense set with no point spectrum and a dense set with no absolutely continuous spectrum, then these sets are G deltas automatically, and then the intersection is generic, which means that generically an operator, a unitary operator, has singular continuous spectrum. And that's kind of surprising, because usually what happened, classically when you look at dynamical systems, you look at integrable behavior, which is a pure point spectrum in ergodic theory, or you look at mixing chaotic behavior. Chaotic behavior means absolutely continuous spectrum. And then there is this large part, which is much larger than anything on the boundary, which is singular continuous. That's a typical case, and also for operators. It's just a little bit switched, that the pure point spectrum least often is associated to randomness. If you take random operators, for example, then you have this localization, or then you have kind of a absolutely continuous cases, usually just ballistic motion, where the Fourier coefficients decay. Fourier coefficients are essentially telling you about the return probability, both here and here. Here you return regularly back, with a almost periodic way you return back, and here you get mixing. So if you have a set, it will get mixed up and never returns back to itself. While here it's a little bit a different picture, but the mathematics is the same. We have just the question, what happens with these operators, what happens with the spectral measures. And this can be looked at in various categories of dynamical systems, classes of dynamical systems. Maybe the first class, the most obvious, is just a set of automorphisms of a probability space, which is just measure-preserving transformations, invertible transformations of a probability space. And then you have a natural metric, you have a weak metric, or you have a strong metric, and you can see what happens generically. And there is a result of Katok-Stepin, which is kind of related to this Oxtoby-Ulam. In some sense, it has been, unified later. But the singular continuous spectrum is generic, which means weakly mixing is generic. So ergodic especially is also generic, which is quite nice. And then there is the volume preserving homeomorphism, which is in spirit very close to the automorphism case, where this Oxtoby-Ulam, that's maybe even earlier. Oxtoby and Ulam worked here at Harvard as junior fellows and got that result after years of work. And it was also, Halmos has kind of then related it with weakly mixing later, but also we can reformulate that a singular continuous spectrum is generic. I kind of gave a simple proof in '98 using this Wonderland theorem. The Wonderland theorem allows you to do this very quickly. And I just should mention also, I was actually working on this last theorem of Manier 25 years ago. I thought this is kind of something which one maybe could do. Manier had this, it's still unproven statement for Hamiltonian maps of symplectic diffeomorphisms of a symplectic manifold that in the C1 topology, either you have hyperbolicity or then you have zero Lyapunov exponents almost everywhere. It's a little bit surprising because that's what we don't expect in the smoother category. The smoother category, you have this picture which is completely open. There's coexistent picture that you have if you have a system like this, right? There's kind of a mixed chaos, there's chaotic motion and there's almost periodic motion intermingled, and probably there are sets of positive measure. That's what one knows by Kame theory, where it's almost periodic, which probably is even dense, and there is a set which is weakly mixing, which we don't know whether this exists in general, but it definitely, exists on positive measure. It definitely exists kind of by these genericity pictures on kind of some special subsets, and then you have the absolutely continuous mixing case, the Pesin region, where you have positive Lyapunov exponents, positive entropy. So when you have C2, then you have the Pesin formula already, which tells you that the Lyapunov exponent, the maximal Lyapunov exponents positive on some set of positive measure implies positive entropy. It's completely open, this kind of thing. And also here, this last theorem of Manier, which is the C1 category, that's also open. But the closest which one has got to is the Bochi-Viana theorem, which says that either in the volume preserving case, this last theorem of Manier has been confirmed. So it's kind of generically, you have either hyperbolicity, hyperbolic behavior, or you have almost everywhere zero Lyapunov exponents. Completely different what you would expect in the smooth case. But in the smooth case, what is really kind of the difficulty is to establish that we have positive Lyapunov exponents. Maybe even all the time, if you are not either in the integrable case or you are not in the Anosov case, hyperbolic situation like the geodesic flow on the surface of negative curvature, or here the geodesic flow on the sphere. That's integrable ellipsoid, and here the geodesic flow on a hyperbolic surface. So hyperbolic space is hyperbolic, ergodic. So there are other things one can, invariant measures, that's something I have worked on also during my postdoc time. And so what happens is, there's a result of Parthasarathy, which says generically you have ergodicity, a generic invariant measure is ergodic, but also here, just by general principles, you have a generic measure is actually weakly mixing. We have also worked, I've worked with Bertholf on differential equations on the torus, and so there what you have is this fxy is a time change. So you start with kind of an irrational rotation on a donut, and then what you do is you just change the time depending on x and y, which makes the kind of return time that's similar to here when you look at induced system. You just change the return time, and that can produce weak mixing. Not mixing, but weak mixing. So generically we have weak mixing, and we showed even that it's generically zero-dimensional by using periodic approximation, which is a great tool of Katok-Stepin in that context. By the way, I'm interested now kind of more in quantum calculus, meaning finite dynamical systems. So, and then you can ask yourself, what does it mean to be generic? What does it mean to be generic? And what is definitely kind of important is kind of you have a sequence of dynamical systems, finite dynamical systems, and you look how fast you can approximate a certain feature. This is about the induced system. This is very interesting. It is something which I have not published, but it's something which just immediately follows from this Wonderland theorem and the fact that one knows that there's a dense set of weak mixing, which is kind of a result ergodic theorists like Friedman have shown. And it's also interesting from the point of view of algebra, because the sets A, such that A is equal to bt delta B, these are called coboundaries. So these coboundaries are actually meager, they are rare. Most of the sets you cannot write like that. Most of the sets you cannot write as coboundary, the derivative, which is really kind of interesting. So you can ask what happens with the cocycles over coboundary. That's a cohomology group, and that that's an uncountable group. It's quite a complicated group. So it's very hard in general if you have a transformation, even an irrational rotation, to decide whether a certain set is a coboundary or not, a measurable set is a coboundary or not. But interesting. There would be other things to mention, like billiards, what happens typically in a billiard, and also there we would kind of expect that for a typical convex smooth billiard you have both behaviors. You have some KM behavior like at the boundary, around elliptic points, and then we have the pace-in region, which is expected to nobody has even one example of a smooth convex billiard with in the plane with a positive Lyapunov exponents on a set of positive measure. And then maybe there is also this set where we have singular continuous spectrum. This is completely open whether this can happen. I know just only on tori I can take a calm torus and perturb the Hamiltonian system a little bit so that I have weakly mixing, but that's not a set of positive measure. That's just, on one. You can perturb it such that on one torus, finitely many tori, we can achieve weak mixing, but that's zero measure. So, but the weak mixing can happen for volume preserving systems like these differential equations from the torus shows. So you can have, so here we just look at the differential equation on the torus itself. It can happen that you have this weakly mixing, which is interesting because it cannot happen on the sphere, for example, by Poincaré-Bendixson. So on a sphere, the behavior is either a limit cycle or a fixed point, and but on a torus you can have this almost periodic behavior or weakly mixing behavior. And Kolmogorov asked whether it's possible to have mixing behavior. That's not possible in 2 dimensions, but might be possible in 3 dimensions. There are just no examples. No. Okay, that's what I wanted to say today.